Hello and welcome to this keynote talk. My name is Dinesh Krishnamurthy and today I'm going to be talking about optimal resource allocation using distributed feedback-based real-time optimization, where the key idea that I would like to present is how to transform a Lagrangian distributed optimization problem into several local feedback control problems coordinated by a central coordinator. Increasing use of computer-aided decision-making tools have led to the tight integration of the digital and physical components, commonly known as cyber-physical systems. And these are now commonly used in modern chemical processing industries. As such, individual units and processing equipments are already automated and operated efficiently in a wide range of industrial applications. With increasing use of automation and optimization tools, several cyber-physical systems need to collaborate to achieve a common goal. Now, such a network of cyber-physical systems ranges from the plant level to a multi-enterprise level, where there are complex interconnections of material and energy flows between different unit operations or even between different processing plants. So with increased focus on sustainability and flexible manufacturing, such large-scale interconnected systems are becoming more and more common these days. For example, in eco-industrial parks and industrial clusters, the different processing and manufacturing companies may share resources in the form of material and energy in a mutually beneficial manner to reduce waste, to increase operational efficiency, and also to meet, say, regulatory requirements. Now, this is commonly referred to as industrial symbiosis, and this is seen as a key driver for sustainable manufacturing. Now, in an eco-industrial park with different chemical processing companies, a common utility hub may be used to allocate the shared resources in order to reduce the utility costs. This can be, for example, a steam from a common heating station that is allocated to different processing plants. Or, for example, byproduct from one company may be used as raw material for another company in order to reduce material waste, or surplus heat from an industrial cluster can be recovered using, say, for example, a heat exchanger network and used for local district heating or for, say, greenhouse farming to reduce energy waste. Another example is modular manufacturing systems. Now, modular manufacturing functionally partitions these different operations into reusable modules. And plug and play of the different modules increases flexible manufacturing and enables production of multiple products with different product specifications from the same facility. So as the process industry is embracing concepts such as industrial symbiosis and modular manufacturing, this creates new challenges for online process optimization. Such large-scale systems have some special structure since these commonly arise from linking different subunits together in one form or the other. So decomposition methods exploits such special structure to divide the optimization problem into different subproblems that are then coordinated towards the uh, overall system-wide optimal solution by a master problem or a master coordinator. Now, optimal resource allocation and coordination among the different companies in an industrial symbiosis requires information about the process in the form of models, real-time measurements, local constraints, and economic objective. Now, sharing of such information across the different organizations may not be desirable due to several reasons, such as intellectual property rights, trade secrets, and market competitiveness. Similarly, in modular manufacturing systems with plug and play modules, it is desirable to have integrated control and optimization tools with each module, which must seamlessly coordinate with the other modules that are in use. As such, distributed optimization is a promising framework for such large-scale systems where the different subproblems are locally solved with limited information sharing, and a central coordinator coordinates the different subproblems in order to compute the system-wide optimal operation. So let us consider a generic optimization problem as shown here. We consider n subsystems that are exchanging m shared resources. So the decision variables of subsystem I are denoted by xi. The local objective of each subsystem is given by fi xi. Each subsystem may also have local constraints that are denoted by this set calligraphy xi. And the shared resource constraints are denoted by the sum of AI xi that must be equal to B. Now, without loss of generality, we can assume that the shared resource may either be consumed or produced by the different subsystems. So the optimization problem here has a specific structure, as in the overall cost of the overall cost is the sum of the individual local costs, and the shared resource is the only constraint that couples the different subsystems together. In order to show how to decompose this kind of problem, let me first quickly give an introduction to the basic primal and dual decomposition techniques. So in primal decomposition, we directly allocate the shared resource such that the ith subproblem receives Ti amount of the shared resource. And then we solve the subproblems by fixing Ti and the master problem that is as shown here. Now the sum of the auxiliary variables Ti that we have here must add up to B, thus ensuring that the shared resource constraint is satisfied. The master problem then computes the new value for these auxiliary variables Ti that tells us now how to reallocate the shared resource among the different subproblems. And this is solved iteratively until we find the optimal values for these auxiliary primal variables Ti. So primal decomposition has an economic interpretation. And the economic interpretation is that the different subproblems report the price they are willing to pay for the shared resource, and the master coordinator directly allocates the shared resources accordingly. Now, the benefit of this approach is that the shared resource constraints remain feasible throughout these iteration rounds. However, this approach often requires that the subsystems share additional knowledge about the local constraints to the master coordinator in order to ensure that the allocated resource is feasible for the subproblems here. And this is given by this calligraphy TI. Right. So therefore, this approach may not be suitable for industrial symbiosis where data privacy is an issue and we don't want to share information about our local constraints. Okay, so in dual decomposition, what we do is we relax the coupling constraint and bring it to the cost by multiplying it with its Lagrange multiplier lambda. So, and then we also have these additional constraints, which are these different local constraints. Now we see that this optimization problem is additively separable for a given Lagrange multiplier lambda. We can then write each subproblem for a given Lagrange multiplier as minimize Fixi plus lambda times Aixi, subject to these local constraints here given by this calligraphy xi. Okay, so now each subproblem can be solved in parallel for a given Lagrange multiplier, and the master problem is then given by this problem here, which computes the new the new Lagrange multipliers. It can be seen that the subgradient of the master problem is nothing but the coupling constraint itself. Therefore, we can update the Lagrange multiplier using a subgradient descent step with a step size alpha that is as shown here. So what we see is that for a given Lagrange multiplier, the different subproblems solve the local optimization problem, and using the residual of the shared resource constraint, the central coordinator then updates the shadow price using the subgradient method. The subproblems are then solved using the newly updated Lagrange multipliers again, and this is solved repeatedly until some stopping criteria is met. So this is the so-called dual decomposition framework, and it is also known as Lagrangian decomposition, and this was introduced in the 60s. Okay, so the Lagrangian decomposition framework also has a nice economic interpretation, where the Lagrange multipliers lambda is the shadow price of the shared resource. So basically, the goal of the central coordinator is to find the equilibrium price for the shared resource such that the supply matches the demand in this micro market setting. So in other words, when the supply of the shared resource increases, the master coordinator decreases the price in order to encourage consumption by the subsystems. Similarly, if the demand for the shared resource increases, the master coordinator then increases the price, the shadow price lambda, to discourage consumption of the shared resource. Unlike primal decomposition, this approach does not require information about the local constraints, and therefore these local constraints need not be shared with the master coordinator, which makes it a favorable approach for industrial symbiosis where we don't want to share these kind of local constraint information, right? But it is also important to note that the shared resource constraint may not be feasible until the subproblems and the master problem converges, unlike in primal decomposition. So such a price-based coordination approach has been studied for several RTO problems by several research groups, and it was noted that the practical use of such decomposition methods are rather low, and it's not used as much as widely in practice. So as noted in this recent publication here, the main reason for this is attributed to the computational cost of iteratively solving the subproblems and the master problems. Right, that means that the subproblem must be repeatedly solved several times before the optimal solution is computed. So there have been some important developments in the field of distributed optimization to reduce the number of iterations or communication rounds between the master problem and the subproblems. For example, instead of using the simple gradient descent step in the master coordinator, one can use an accelerated gradient descent step to speed up the convergence by using some of these Nesterov type acceleration. Alternatively, instead of using just the first order information in the master problem, namely the gradient, one can also use higher order methods to speed up the convergence. So some noteworthy algorithms in this direction include the augmented Lagrangian alternating direction inexact Newton method, known as Aladdin, the quadratic approximation method, and the second order multiplier update method. So the figure here that recently appeared in an article in Computers and Chemical Engineering nicely summarizes the number of communication rounds needed by these different methods compared to the richness of data that is exchanged between the master and the subproblems. So in real-time optimization, the correctness of computation is also a function of time. So what do I mean by this is that a meaningful application requires that the solution to the optimization problem is available when I need it. So we see that most of the developments to address the computation time in distributed optimization has predominantly been aimed at reducing the number of communication rounds between the master and the subproblems. And although these are very important developments, the computational burden of solving the subproblem itself still remains. And this is what I would like to focus in this talk. So in order to circumvent the need to solve numerical optimization problems online, there has been developments in the so-called feedback optimizing control framework, where the key idea is to transform the economic optimization problem into a feedback control problem. In other words, we need to find some control variable which when we control it to a constant set point leads to optimal operating conditions. Now, since its inception in the 1980 by the work of Morari, Arkunan, and Stephanopoulos, several works have appeared in this direction of feedback optimizing control. Now, these methods are either based on controlling a single measurement, a linear combination of measurements, the steady state cost gradient, because that leads to achieving the stationarity condition and hence the necessary condition of optimality, or even a linear combination of gradients as the optimizing control variable. So feedback optimizing control in general is more suited for unit operations or for small scale processes. In large scale systems, it becomes easier to design such kind of feedback optimizing control for small subgroups of processes or for small units for small subunits, right? So this typically leads to a decentralized control structure where some clusters of operating units are optimized locally without any kind of coordination. However, when the system is coupled in one form or the other, system-wide optimal operation does not necessarily result from the aggregates of individual operating units in a decentralized fashion. So to address this, in distributed feedback-based RTO, we don't want to find just any optimizing control variable, but we want to find an optimizing control variable that is a function of the shadow prices such that the master problem can be used to coordinate the local feedback controllers. So what I mean here is that for a given shadow price, each subsystem has some local feedback optimizing control loops that optimizes the local subsystem for a given shadow price. And since the control variable is now a function of the shadow price, now as the master coordinator updates the shadow prices, this would then lead to the system-wide optimal operation. Right, so the main question here is then what should be the optimal optimizing control variables, right? So what should be in these blue boxes? What should we control? So to answer this, let us go back to the optimizing problem with the relaxed coupling constraints. That is the dual decomposition framework, where each subproblem is expressed as a function of the Lagrange multipliers or the shadow prices, as shown here. So for stationarity condition in each subproblem, we need that the gradient of the cost function plus ai times lambda must be equal to 0. So this is when we have the necessary condition of optimality. So using this idea, we can then say that the local optimizing control variables in each subsystem must be given by the cost gradient plus ai times lambda, which must be controlled to a constant set point of 0, such that for a given shadow price, the local subsystems satisfy the necessary condition of optimality. Now, since the steady state cost gradient is not a readily available measurement, this must be estimated in each subsystem. So in each subsystem, using only the local information, such as the local models and the local measurements, we estimate the steady state cost gradient and control the local optimizing control variables to a constant set point of 0. And at every time step t, using only the shared resource residual information, the master coordinator then updates the shadow prices using the subgradient method. So note that the subgradient method in the master coordinator is nothing but a simple integral controller, right? So this drives the coupling constraint to 0, and by this, the price is updated if the supply does not match the demand, and the shadow price converges when the coupling constraint is satisfied. Okay, so by doing so, what we have done is we have now transformed the Lagrangian decomposition framework or the price-based coordination framework into several local feedback control problems coordinated by the same master coordinator. So instead of just the Lagrange multiplier, we can also consider the augmented Lagrangian, where in addition to the relaxed coupling constraint, we also add an additional quadratic penalty term, as shown here, with rho over 2 as the penalty factor. So in each subproblem, we then minimize this augmented Lagrangian, for which the stationarity condition is given by this expression here. So this is the same as what we had before, with this additional term that represents the residual of the shared resources, which we denote by this variable R. So in this case, the local optimizing control variable is given by the cost gradient plus ai times lambda, plus this additional term rho times ai times the residual of the shared resource R. So by adding this additional quadratic penalty term, the nice thing is that we can now show that the distributed feedback-based RTO converges to a stationary point of the overall system as time t goes to infinity. And this convergence analysis was recently published in the Journal of Process Control. Okay, so the proposed approach relies on the cost gradient, which must be estimated online. Luckily, there is a rich literature on gradient estimation methods, which are either model-based or completely model-free. So, for example, Srinivasan and co-workers have also published a comparison of the different model-based and model-free gradient estimation methods, and any of these model-based or model-free gradient estimation methods can be used in our framework. One could also use a combination of the model-based and model-free gradient estimation method in this framework. Okay, so far we have considered a problem formulation with a specific structure, namely an additive cost with linear coupling constraints. Although this may seem a bit restrictive, surprisingly, a large number of optimization problems can be expressed in this form. Right. So in any case, nonlinear constraints can also be easily handled with the proposed framework, where now the local optimizing control variable is given by the cost gradient plus the coupling constraint gradient times lambda. So basically, again, we're using the idea of finding the stationarity condition for this subproblem as a function of lambda, the shadow price, which the master problem can update, thereby coordinate the different subproblems. Okay, so now we apply our proposed distributed feedback optimizing control on an offshore oil and gas production problem. So here the different subsea wells that are producing from different reservoir sections are operated by different companies, but they share the same topside processing facilities. So this can be seen this can be seen as an industrial symbiosis system, right? So inspired by this real life example, we now consider an example where there are 10 gas lifted subsea wells, and we assume that these are operated by 4 different companies. So we group these wells into like 3 wells that are operated by company 1. These set of 3 wells are operated by company 2. These 2 wells are operated by company 3, and these last 2 wells are operated by company 4. So these wells, they all share the same topside processing facilities, which couples these different subsystems together. So the overall objective is to maximize the revenue from total oil production and minimize the cost of gas compression that is used for gas lift. So in gas lifted wells, gas is compressed in these topside processing facilities and is injected into the wells to reduce the hydrostatic pressure drop in the wells and hence boost production. So the lift gas here is one shared resource that must be optimally allocated among the different subsystems, and we assume that there are limitations on the total available gas that is available for gas lift. Okay. So similarly, the topside processing facility may also have capacity limitations. For example, how much gas the topside processing facility can handle. So as such, the total gas that is produced by the different subsystems must be less than the maximum processing capacity, which is another coupling constraint. So we have an optimization problem with 4 subsystems and 2 shared resources, which we solve using the proposed framework. So in each subsystem, we use a model-based gradient estimation, and we use a simple PI controller to drive the local optimizing control variable to a constant set point of 0. Right. So and then at each time step t, the subgradient method is used in the master coordinator to update the shadow price for the 2 coupling constraints. Okay, so now here we show the simulation results where we compare the performance of the proposed approach, which is shown in these black solid lines, with the ideal optimum, which is obtained by numerically solving the overall optimization problem as a single centralized optimization problem. And this is shown in these red dashed lines. Right, so then this ideal optimum serves as the benchmark to compare the performance of our proposed approach. So the left subplot here shows the total oil production and the total gas production and also the total gas lift injection rate as the feed disturbance varies over time. So the maximum capacity constraint and the maximum available gas lift are also shown in these gray dotted lines in these 2 subplots here. And the right subplot shows the absolute difference between the proposed approach and the ideal optimum. And from the simulation results, we can see that the proposed distributed feedback optimizing control framework is able to drive the process to its optimal steady state operation without the need to solve numerical optimization problems online. And we have also solved this in a distributed fashion with a master coordinator that coordinates these different problems such that we don't have to share information amongst these 4 different companies. So to summarize, in this work, we presented a distributed feedback-based optimizing control approach where the Lagrangian decomposition framework was transformed into several local feedback control problems that is coordinated by a master coordinator. We presented a general framework where any model-based or model-free gradient estimation method can be used for the gradient estimation. Any set point tracking controller such as PID or MPC may be used in the local optimizing control loops. And the developments in the distributed optimization literature that focuses on reducing the number of iterations between the master problem and the subproblem can also be used along with the proposed framework, where we replace the subgradient method with, say, for example, the accelerated gradient methods or the second order methods to update the shadow prices. So for a more detailed discussion on this approach, and especially using the augmented Lagrangian and to show the convergence analysis, I would also like to point out to the recent paper that was published in the Journal of Process Control. So with this, I would like to conclude my talk, and thank you for your attention.